Hey there, and welcome to Dev with a Lens, the space where tech meets creativity. I'm so glad you're tuning in. Whether you're into code, cameras, or a little bit of both, you're in the right place.
Welcome to the deep dive. Today we are plunging into a topic that sits right at the core of modern Java applications, but one that many developers find, well, challenging: concurrent programming.
Yeah, it's really about writing code that seems to do multiple things at once.
Exactly. And while that's essential for performance, it definitely brings its own unique complexities.
Oh, absolutely.
Yeah.
It's a space where even, really seasoned developers can run into these incredibly subtle bugs, stuff that's just really hard to reproduce.
Yeah.
So understanding the foundations is, well, it's absolutely key.
For this deep dive, we've been digging into let's say, a classic foundational text on concurrent programming in Java. It's really packed with essential wisdom. And our mission today is basically to distill that for you, unpack the core challenges, get a handle on the risks involved, and look at the tools and techniques Java offers to manage concurrency safely and effectively.
And importantly, this isn't just for people who are like explicitly writing new thread. As you're going to see, you're interacting with concurrent code pretty much constantly. Maybe without even realizing it.
That's such a crucial starting point, isn't it? Threads are just everywhere in the Java world. Let's unpack that. Why threads?
Right. So threads kind of evolved from the older idea of processes. But instead of a whole separate process with its own memory space, threads give you multiple sort of independent streams of control within a single process.
Okay.
And the big deal there is they share resources. Especially memory.
And that sharing, that's where the power comes from, right?
Yeah.
Leveraging multi-core processors, but it's also where all the complexity creeps in.
Exactly. Exploiting that hardware parallelism is a huge driver. You get performance, but you pay for it.
Yeah.
And the point you made about using them unknowingly, super important.
Yeah.
The JVM itself starts background threads. For garbage collection, finalization, even just running your main method happens in a thread.
So right out of the box, you're in a multi-threaded world.
Yep. And then think about the frameworks you use all the time. Older UI toolkits like AWT, Swing. They have dedicated event threads. Timers use background threads. Web servers running servlets. Or distributed systems like RMI.
They're all managing pools of threads, right?
Yeah.
And they just call your code your servlet's service method, your remote method on one of those threads.
Precisely. Which means any code that gets called from those framework threads, and that's likely most of your application logic, it has to be thread safe.
Wow. So the burden's really on the developer, even if you never intended to write concurrent CAD.
Yep. You are working in a concurrent world, like it or not.
Okay, so if you write Java code, you really need to get this stuff. And moving from that single-threaded mindset, you hit these new problems. Which brings us, I guess, to the core challenges. Safety versus liveness.
That's the fundamental trade-off, really. First up is thread safety. This is all about making sure nothing bad ever happens. Mostly. That means shared mutable state doesn't get corrupted when multiple threads mess with it at the same time. It's not a new goal exclusive to concurrency, but threads introduce brand new ways for things to go wrong.
Like data getting mixed up or just plain inconsistent?
Exactly. Then the other side of the coin is liveness. This means something good eventually happens. Your program actually makes progress. It doesn't just get stuck.
Right.
And just like threads bring new safety hazards, they also bring new ways for things to just stall or fail completely.
Getting into weird infinite loops or waiting forever for something.
You got it. So let's dig into the safety hazards first. The source really emphasizes that safety is non-negotiable. A classic problem here is race conditions.
Yeah, this feels like the one everyone hits first when they start playing with threads without quite knowing what they're doing. It's when the outcome just depends on the luck of the draw, the unpredictable timing between threads.
The source uses a great analogy. Imagine meeting someone at the Starbucks on University Avenue, but there are two of them. You check Starbucks A, they're not there. You start walking to Starbucks B. Meanwhile, maybe they just arrived at A, checked, didn't see you, and started walking towards B themselves.
Huh. You could just keep walking past each other forever.
Exactly. The core issue is your observation they weren't at A. It became stale the moment you acted on it by hitting to B. By the time you reach B, the situation at A might have totally changed.
Oh, I see.
And that invalidation of observations is typical of race conditions in code. You check something, like if x equals 5, but by the time you execute the next line based on that check, another thread might have changed x.
Okay, that makes sense. Now, another one you mentioned, which sounds really subtle, is visibility.
Yeah, this one really, really trips people up. It's
Yeah.
quite counterintuitive. In a single thread, you write to a variable, you read it right after, you get what you wrote.
That
Simple.
makes sense.
But in a multi-threaded world without proper synchronization, there's just no guarantee that a change made by thread A will be seen by thread B immediately.
Yeah.
Or even ever. Or in the order it was written.
Right, really? In the wrong order.
Yep. Changes can hang out in thread A's local cache, or the processor might reorder instructions for performance. The no visibility example in the source is pretty stark.
What does it show?
It has a reader thread looping, waiting for a ready flag to become true, and then it prints a number. Without synchronization, that reader thread might never see the ready flag change and just loop forever.
Ouch.
Or, even worse, due to reordering, it might see the ready flag become true before it sees the updated value of number. So it might print 0, the default, instead of the intended value like 42.
Wow. Okay. So it's not just about operations being atomic. It's about whether memory changes actually become visible across different cores or caches and in the right sequence.
Exactly. The Java memory model, which maybe we can touch on later, defines the rules here. But the takeaway is just accessing plain variables between threads isn't automatically safe or consistent.
All right, so these hazards are serious. How do we actually achieve safety then? What are the main tools in the toolbox?
Well, the most fundamental one is synchronization. In Java, that usually means the synchronized keyword, or maybe the more flexible lock interface they added in Java 5.
Okay, synchronized, what does it actually do?
It gives you two crucial things. First, mutual exclusion, meaning only one thread can be inside a particular synchronized block or method at a time for a given object lock. Second, visibility changes made inside a synchronized block are guaranteed to be visible to other threads that later acquire the same lock.
Got it. The source mentioned using narrow synchronized blocks.
Right. Think about that servlet example again. If you just slap synchronized on the entire service method.
You've basically bottlenecked your whole web app down to one request at a time. Kills scalability.
Exactly. So instead, you only synchronize the absolute smallest chunk of code that needs exclusive access to shared mutable state. You definitely avoid holding locks during, say, long I/O operations or anything that doesn't touch that shared data.
But you have to be careful not to make the block too narrow either, right? Like if you need to check a value and then update it, those probably need to be inside the same synchronized block.
Precisely. Finding that right granularity is key. And another potential pitfall is what's called client-side locking, especially with older collections like Vector.
How does that go wrong?
Say you have a vector instance, myVector, and in your code, you write, synchronize myVector, loop through it, thinking you're safe.
Yeah, seems reasonable.
But that only protects access within that specific block. Nothing stops some other piece of code somewhere else from accessing myVector without synchronizing on it.
Ah, I see. So your lock doesn't actually guarantee exclusive access.
Right. And you can still get errors. Maybe another thread removes an element between your myVector.size, call inside the loop condition, and your myVector.getI, call inside the loop body, boom, array index out of bounds exception.
So the lock has to guard all paths that touch the shared mutable state.
Exactly. And a common good practice is to guard an object's state, not with its own intrinsic lock, but with a dedicated private lock object, like private final object lock, new object.
Why is that better?
It prevents external code from accidentally grabbing your object's internal lock and potentially causing interference or even deadlocks you didn't anticipate. It encapsulates your locking strategy.
Okay, that makes sense. Now, beyond explicit locking, is there sometimes a way to just sidestep the whole synchronization issue?
Absolutely. And it's a really powerful technique, immutability.
Meaning the object just can't be changed.
Exactly. If an object state cannot change after it's constructed, then multiple threads can read it all day long concurrently without any synchronization needed. Safety is built in because there's no shared mutable state to protect.
Okay, how do we properly define immutable here? What are the rules?
The source lays out a few key points. 1, the object's state can't be modified after construction. 2, all its fields should be declared final. 3, it has to be properly constructed, which crucially means this reference doesn't escape the constructor before it's fully built.
What about final fields that point to objects that are mutable, like a final list? Does that break the immutability of the containing object?
Not necessarily for the container itself. Think of the Three Stooges example from the book. It might have a final set string field holding the names. That set could potentially be modified if someone got a reference to it.
Right.
But the Three Stooges object itself is immutable if the set of stooges it represents is fixed once it's created. The immutable object controls access. So the field reference is final, meaning it always points to the same set instance, and the state of the Three Stooges object, which Stooges are included, doesn't change.
Okay, I think I follow. The container's identity and core state are fixed, even if a component it holds could be changed if you weren't careful.
Right. And a really important pattern emerges here. You update program state not by changing an immutable object, because you can't, but by creating a new immutable object with the new state and replacing the reference to the old one.
So using final for fields is a really strong signal about immutability and makes things easier to reason about.
Totally. It's good documentation and prevents accidental changes. Plus, immutable objects get this special guarantee from the Java memory model called initialization safety.
What's that?
It means once an immutable object is properly constructed, any thread can access it safely without needing any extra synchronization, even if the reference wasn't published using, say, volatile or a lock.
Whoa, that's a big deal. No volatile needed just to see the final fields correctly.
Precisely, for the immutable object itself. Now, if those final fields point to mutable objects, like our set example, you still need synchronization if multiple threads might try to modify the state of that mutable set.
Okay, got it. That naturally leads to safe publication. You mentioned visibility issues before. For mutable objects, just making the reference visible isn't enough, right?
Correct. You have to ensure that both the reference and the object's internal state, as it was when it was published, become visible to other threads atomically.
How do you guarantee that?
The source lists several reliable ways. Initializing the reference in a static initializer works. Storing the reference in a volatile field, or an atomic reference, is another common way.
Okay.
Storing it in a final field of a properly constructed object also works that links back to initialization safety. Or, a really practical one, just putting the object into a thread-safe collection like a ConcurrentHashMap or a BlockingQueue.
Ah, so just dropping it into ConcurrentHashMap handles the safe publication for you.
Yes. The collection's internal synchronization ensures that happens before relationship. When another thread gets the object out of the collection, it's guaranteed to see the state the object had when it was put in.
Nice. Okay, another technique mentioned is building thread-safe classes by delegating thread safety.
Yeah, this is super common. You build a class, but its state is actually held and managed by underlying components that are already thread-safe, like using an atomic long inside your class to handle a counter safely.
Like the counting factorizer example.
Exactly. This works great if your class doesn't need to maintain any extra rules or invariants that span across those independent thread-safe parts.
Can you give an example where simple delegation isn't enough?
The number range example is perfect. Imagine a class tracking a lower and upper bound, maybe with two atomic integers. The key rule, the invariant, is that lower must always be less than or equal to upper.
Okay.
Now, updating lower is atomic and updating upper is atomic, but what if you need to increment lower and decrement upper in one logical step while ensuring they don't cross? Just calling methods on the atomic integers separately isn't enough.
Ah, because another thread could sneak in between the two updates and see an invalid state where lower-upper temporarily.
Precisely. To maintain that compound invariant, you'd likely need an external lock guarding both variables, ensuring the check and the updates happen as one atomic unit. Simple delegation fails when invariants cross state boundaries.
Okay, so delegation works when the safety rules are fully handled within the delegated components.
Exactly. And sometimes you can even go a step further and publish underlying mutable state if your class doesn't impose extra constraints on it. The publishing vehicle tracker example does this.
How does that work?
It uses a concurrent hash map where the values are mutable safe point objects representing vehicle locations.
So the map itself is thread-safe for adding mere moving vehicles, and the safe point objects hold the changing coordinates.
Right. And critically, the SafePoint class itself must also be thread-safe. It needs to provide a safe way to get, say, both x and y coordinates together, perhaps by copying them under an internal lock.
Why is that important?
To prevent inconsistency. If a caller just called getX, then getY separately, another thread might update the location between those calls. The caller would get an X from one time and a Y from another, a location the vehicle might never have actually occupied.
Gotcha. So the safe point guarantees atomic access to its own state.
Yes. And the publishing vehicle tracker relies on the concurrent hash map for the collection safety and the safe points for the location safety. Callers might get references to these mutable safe points, and they can change, but the tracker itself doesn't need to manage those changes because the safe point handles its own thread safety. This design is okay only if the tracker doesn't care when a point's location changes internally.
Okay, that makes sense. So we've covered a lot about safety, making sure nothing bad happens. What about the other side? Liveness hazards, when things just stop making progress?
Right. This is when your program gets stuck. It's waiting for something that's never going to happen. Yeah. The main types are Deadlock, Starvation, and Livelock.
Deadlock's the classic one everyone pictures, right? Two threads waiting for each other.
It is. The textbook resource-based deadlock. Thread A has lock 1, needs lock 2. Thread B has lock 2, needs lock 1. Oops, they wait forever.
A circular dependency.
Exactly. But there's a subtler one too. Thread starvation deadlock. This can happen with, say, fixed-size thread pools.
Oh.
You imagine a task running in a bounded pool, submits another task to the same pool, and then immediately blocks, waiting for that second task's result.
Okay.
Now, what if all the threads in the pool end up doing this? They're all busy running tasks that are just waiting for other tasks stuck in the queue.
Which can't run because all the threads are busy waiting. Deadlock.
Exactly. Bounded pools and tasks that depend on other tasks submitted to the same pool. That requires very careful thought.
And starvation is slightly different.
Yeah, starvation is when a thread could proceed, but it's just perpetually denied access to a resource it needs. Maybe it keeps losing the race to acquire a lock to less polite threads, even though the lock becomes available repeatedly.
Unlucky thread.
Pretty much. And Livelock is, well, it's almost funny if it weren't so frustrating. The thread isn't blocked, it's actively doing things, but it makes no actual progress.
Like running in circles?
Kind of. Think of the poison message problem in messaging systems. A worker picks up a bad message, tries to process it, fails, the transaction rolls back.
Message goes back on the queue.
The same worker, or other, picks it up again, fails again, rolls back again. It's constantly busy, but it's stuck processing the same bad message over and over. That's Livelock.
Okay, so how do we try and avoid these liveness problems?
Well, one really powerful principle, especially for fighting deadlock, is making open calls.
An open call, what's that?
It means when your code, while holding one of its own locks, calls a method on another object, especially one outside your control, you should release your lock before making that call if possible. Or just don't hold the lock during the call.
Why does that help?
Because if you hold your lock and call into some unknown code, you have no idea what locks that code might try to acquire. It could try to acquire another lock that you also sometimes hold, potentially leading to a deadlock cycle that's really hard to see. Making open calls breaks that chain.
So do your locked work, release the lock, then call the other object's method.
Ideally, yes. It simplifies reasoning about lock ordering. Another useful technique, especially with the explicit lock interface, reentrant lock, is using timed lock attempts.
Instead of just waiting forever if the lock isn't available.
Exactly. Lock.tryLock, timeout unit, lets you attempt to get the lock for a limited time. If you get it, great. If not, it returns false after the timeout.
What do you do then?
You can then choose. Maybe you release any other locks you managed to get, back off for a bit, perhaps a random delay to avoid multiple threads retrying in lockstep, which could cause Livelock and then try again. Or maybe you just give up and report a failure. It's crucial for tasks that have time limits.
Right, like calling an external web service that might be slow. You don't want to wait forever.
Precisely.
Okay, we've sketched out the hazards, safety issues like race conditions, visibility, and liveness issues like deadlock. Now, let's talk about the reinforcements that arrived in Java 5.0, the java.util.concurrent package.
Yes, JUC. This is a massive leap forward. It provides these really robust, highly optimized building blocks that make writing concurrent code much simpler and, often, way more performant than trying to do it all manually with just Synchronized.
Starting with things like the concurrent collections.
Absolutely essential. ConcurrentHashMap is the star here. It offers way better scalability than the old synchronized map wrapper or hash table, mainly because it allows multiple reads and even some writes to happen truly concurrently, using clever techniques like lock striping.
Does it let you lock the whole map, though, like for iterating safely?
Generally, no. It doesn't support that kind of client-side locking for exclusive access, but what it does provide are built-in atomic compound operations, like put if absent, replace, remove. These handle common check-then-act scenarios safely and efficiently internally.
And blocking queues are another big one.
Oh yeah, fundamental for producer-consumer patterns. You have threads putting stuff into the queue, and threads taking stuff out, take.
Okay.
If the queue is full, put blocks. If it's empty, take blocks. Implementations like link blocking queue or array blocking queue handle all that synchronization for you. It beautifully decouples the producers from the consumers, and they're the heart of the executor framework.
Right. The executor framework, that's the modern way to handle tasks instead of manually creating threads, isn't it?
Definitely. You should basically forget new thread runnable.start. The executor framework, using things like Thread Pool Executor, gives you managed pools of worker threads.
Why is that better?
Several reasons. It prevents you from creating unlimited threads if you get a huge burst of requests, which can crash your app. It lets the application degrade gracefully under load. And it gives you knobs for tuning, management, monitoring, things you just don't get with raw threads.
And it works with Callable and Future.
Right. Runnable just runs, doesn't return anything. Callable's like Runnable, but it can return a result and can throw checked exceptions. Okay. When you submit a Callable or a Runnable to an executor service, you get back a future. That future object represents the task's lifecycle. You can use it to check if the task is done. You can wait for it and get the result, which blocks if needed and rethrows any exception the task threw.
Or you can try to cancel it.
Exactly, using future.cancel.
So if you need to kick off several tasks and maybe wait for them all or get their results,
then future is your friend. And methods like executorservice.invocAll are really useful. You give it a collection of callable tasks and it runs them all, returning a list of futures when they're all complete.
is there a timed version?
Yep, invocAll has a timed variant, super useful. The travel portal example is great. Launch requests to multiple airlines concurrently using invocAll. Set a timeout, say 5 seconds. When it returns, you gather the results you got, and it automatically cancels any tasks that didn't finish in time. Keeps the UI responsive.
Nice. The library also has these synchronization aids, right? Higher level stuff.
Yeah, tools beyond basic locks. Semaphore lets you control access to a pool of resources using permits. CountDownLatch is a way for one or more threads to wait until a set of operations being done by other threads completes.
Like waiting for initialization.
Exactly.
Yeah.
And CyclicBarrier lets a group of threads all wait for each other to reach a common barrier point before they all proceed together. These are built on a really clever low-level framework called Abstract Queued Synchronizer, or AQS, which simplifies building these kinds of complex synchronizers reliably.
Okay, shifting gears slightly. What about stopping tasks cleanly? Cancellation and shutdown.
Right. If a task is running off in another thread, maybe via an executor, you often need a way to tell it, please stop. As we said, future.cancel, true, is the way with executors. The true part means try to interrupt the thread if it's running.
But the task has to cooperate, right?
Absolutely. Calling cancel true sets the thread's interrupt status. The task code itself needs to periodically check thread.currentThread.is interrupted, or respond to interrupted exception, which gets thrown by blocking methods like sleep, wait, or BlockingQueue.take when a thread is interrupted. If it doesn't check, it might just ignore the cancellation request.
So cancellation is cooperative. What about shutting down a whole service or application?
That can get tricky too, because of potential race conditions during the shutdown process itself. Imagine trying to log a final shutting down message, but the logging service itself is already partly shut down.
Yeah, that sounds messy.
The source suggests needing strategies like atomically checking a shutdown requested flag and maybe using a counter to allow essential cleanup actions to proceed while preventing new work from starting.
And what are shutdown hooks?
They're threads you register with the JVM using runtime.add shutdown hook. The JVM promises to start these hook threads when it begins a normal shutdown sequence, like receiving SIGTERM, or when all non-daemon threads finish.
What are they used for?
Typically for cleanup. Closing files, flushing buffers, releasing native resources, closing network connections gracefully.
Do they run in any particular order? Or wait for other threads?
No, that's the catch. They can run concurrently with each other and potentially concurrently with other application threads that haven't finished yet. So a shutdown hook needs to be thread safe and shouldn't rely on other application services still being fully functional. A common pattern is to have just one shutdown hook that then calls various cleanup methods sequentially in a controlled order.
Okay, makes sense. We've covered the problems, the tools. Let's zoom out a bit and consider performance. I mean, that's often why we use concurrency in the first place, right?
Yeah.
But it sounds like it has its own performance costs, too.
Oh, for sure. It's always a trade-off. Performance versus complexity versus safety versus maintainability. And a really key point the source makes, echoing good engineering practice everywhere. Beware of premature optimization.
Don't try to make it fast before you know it works and where it's actually slow.
Exactly. Especially with concurrency, trying to hand-roll some clever lock-free thing before you've even measured or used the standard utilities is a recipe for subtle, awful bugs. Don't guess about performance, measure.
So, assuming we do need performance and scalability, what's the guiding principle?
Well, you have to understand Amdahl's law.
That's the one that says your maximum speedup is limited by the part of the job that has to run sequentially, right?
Precisely. Even if 95% of your tasks can be parallelized, that 5% that must run single-threaded puts a hard cap on how much faster you can get no matter how many processes you add. That serial portion becomes the bottleneck.
And what are the actual overhead costs that threads themselves introduce, even when they're running in parallel?
Oh, there's context switching. When the OS swaps one thread off a CPU and puts another one on, it has to save the state of the first one, registers, stack pointer, etc., and load the state of the second. That takes time. Too many runnable threads competing for too few CPUs leads to a lot of context switching overhead.
And memory synchronization isn't free either, using synchronized or volatile.
Definitely not. These constructs often rely on special hardware instructions called memory barriers. These barriers can stall the processor's pipeline, force caches to be synchronized with main memory, and crucially, they inhibit certain compiler optimizations like instruction reordering.
Because the order suddenly matters for correctness.
Right. Plus, all that cache coherence traffic puts extra load on the memory bus, potentially slowing down all cores. So, synchronization buys you correctness, but it costs you performance.
Which means if you want better scalability,
Then reducing lock contention is usually your primary target. Since locks force threads to wait, serialize, the less time threads spend waiting for locks, the more parallel work they can do.
how do you reduce contention?
Couple of main ways. Reduce how long you hold the lock, keep synchronized blocks short. Reduce how often threads need the lock. Or use finer-grained locking. Instead of one giant lock for old data structure, maybe use separate locks for different parts. That's called lock splitting. Or use techniques like lock striping, where you have an array of locks and pick one based on the hash code of the key, like ConcurrentHashMap does.
Spreading the load across multiple locks.
Exactly. Also, try to avoid hot fields, single counters, or pointers that every thread needs to update constantly, creating a bottleneck even with fine-grained locking.
And monitoring is key to seeing if you have contention or other bottlenecks.
Absolutely. Tools like VMstat on Linux or performant on Windows can show you CPU utilization across cores.
Right.
If some cores are idle while others are slammed, maybe you need more parallelism or better work distribution. If all cores are pegged at 100% and you still have lots of threads waiting to run high run queue length, then you're likely CPU bound and might actually benefit from more hardware or maybe tuning thread pool sizes.
Okay. This brings us to maybe the hardest part. Testing concurrent programs. This sounds daunting.
It really is one of the biggest hurdles. The core problem is non-determinism. Concurrency bugs, race conditions, deadlocks often depend on very specific, maybe rare, timing interactions between threads.
So a bug might only show up one time in 1,000 runs.
Or only under heavy load, or only on a machine with more processors than your development box. They can be incredibly elusive. This means testing has to be much more thorough. You need to run tests longer, with more threads, under more varied conditions, just to increase the probability of triggering the bug.
So your standard sequential unit tests are still useful, but they won't catch these concurrency issues.
Correct. They test the basic logic of your components in isolation, which is essential. But you absolutely need dedicated multi-threaded tests designed to stress the concurrent aspects, try to provoke data races, check for liveness problems under load, verify invariance hold when multiple threads are pounding on the code.
And testing things that involve blocking, like waiting for a queue or a latch, must add another layer of complexity.
Oh yeah. Writing a good concurrent test can sometimes be as hard as writing the concurrent code itself. Your test harness needs to manage multiple threads, coordinate their actions, check for expected outcomes, which might themselves be subject to timing issues, and crucially, ensure the test actually finishes reliably. Using things like deterministic termination criteria helps, like in a producer-consumer test. You count exactly how many items were produced and consumed to ensure none were lost or duplicated.
So stress tests are key. Lots of threads, lots of iterations.
Very important for fleshing out safety violations. You also need to think about testing resource management. Can your bounded buffer implementation actually prevent memory exhaustion under load? You might need heap inspection tools to look for memory leaks that only manifest over long runs in concurrent scenarios.
And performance testing concurrent code. Any special gotchas there?
Several big ones. First, garbage collection. If a major GC pause happens during your short benchmark run, it can totally skew the results. You need to run tests long enough for GC costs to average out, or use tools to control or monitor GC. Second, dynamic compilation. The JVM's JIT compiler warms up over time. The first few thousand times a method runs, it might be interpreted or lightly optimized. Later, it gets heavily optimized native code. So you must include a warm-up phase in your benchmark before you start measuring, otherwise you're timing the slow initial runs.
Right. Let it get up to speed first.
And third, the optimizer can be too smart sometimes and perform dead code elimination. If your benchmark computes some result, but then doesn't do anything with that result, the compiler can't optimize away.
It might just remove the entire calculation you're trying to measure.
Exactly. You think you're timing your complex algorithm, but you're actually timing an empty loop. You have to ensure the result of the benchmarked code is somehow used after the timing measurement stops in a way the optimizer can't easily bypass. HE print it, add it to a volatile field, use it in a checksum that's checked later.
Wow. Okay, so testing helps build confidence, but it sounds like it can't guarantee correctness given the non-determinism.
That's the reality. The source really hammers this point home. Testing is essential, but it's not sufficient on its own. You need to combine unit tests, multi-threaded tests, stress tests with other quality assurance techniques. Code review by developers experienced with concurrency is incredibly effective at spotting subtle issues that tests might miss. Static analysis tools can also find certain classes of concurrency problems. It really takes a multi-pronged approach.
Man, we've really gone from the why of threads all the way down to the nitty-gritty of testing them. It's a huge topic.
And honestly, we've just scratched the surface of what's in the source text. It goes even deeper into more advanced areas.
Like what?
Well, things like the fine-grained control you get with explicit locks reentrant lock gives you timed waits, pulled tries, interruptible acquisition, different fairness policies, more options than plain synchronized.
Okay.
How to build your own custom synchronizers using that abstract queued synchronizer, AQS, framework we mentioned. That's how things like Semaphore and CountDownLatch are actually built. AQS provides the core blocking and queuing logic.
Right.
Also atomic variables, atomic integer, atomic reference, etc. And the whole world of non-blocking synchronization using low-level hardware primitives like compare and swap, CAS. These can sometimes offer better scalability than locks under very high contention, but designing correct non-blocking algorithms is extremely difficult.
And underlying all of this
Is the Java memory model, JMM. The really low-level specification that defines exactly what guarantees you get around things like visibility of writes between threads, the ordering of operations, and that crucial happens before relationship that underpins why synchronization works and why things like unsynchronized access or improper publication are dangerous.
Okay, let's try and wrap this deep dive up. We've definitely seen that threads are fundamental in Java. They bring performance potential by using modern hardware.
But they introduce really significant challenges around safety. Nothing bad happens. And liveness, something good eventually happens.
Understanding those hazards, race conditions from timing issues, visibility problems due to caches and reordering, and liveness failures like Deadlock or Starvation, that's absolutely step one.
For sure. And thankfully, Java gives us a pretty rich toolkit to deal with it. From basic synchronized, the powerful guarantees you get from making objects immutable,
to techniques for safely publishing objects between threads. And of course, that whole suite of tools in java.util.concurrent, the collections, the executor framework, the synchronizers.
But just knowing the tools isn't enough. Using them right requires careful design. And as we saw, testing concurrent code is uniquely challenging because of non-determinism. You need specific strategies, stress testing, and you really have to combine it with rigorous code review and maybe static analysis to feel confident.
Yeah, it's really clear that writing good concurrent code isn't just about syntax. It's a different way of thinking about state, about interaction, about timing across potentially many threads of execution.
It's definitely a discipline you have to learn and practice.
So, as you, our listeners, continue working in Java and you are interacting with threads, whether you started them yourself or not, here's maybe a final thought to mull over. Given this interplay between the power of concurrency and its inherent complexity, how will you approach your designs to find that right balance? How do you get the performance you need while absolutely ensuring the safety, the liveness, and critically, the testability of your applications?
That's the question, isn't it? Finding that balance is what leads to truly robust software.
All right, that's a wrap for today. I really hope you found something helpful or inspiring in this episode. If you've got any questions or just want to share your thoughts, feel free to drop a comment or slide into our DMs on Instagram. We're at @devwithalens. Don't forget to hit that subscribe button so you don't miss our upcoming tutorials and conversations. There's so much more coming your way. Thanks so much for tuning in. I'm truly glad you were here. Until next time, take care and keep creating.